Every stream will drain an area of land which is called a drainage basin, or also called a watershed. So these are areas in which the precipitation is collected and drains off into a common outlet, such as into a river or a bay or some other body of water. Each drainage basin is bounded by kind of an imaginary line, which is called a divide. And these are typically clearly visible as sharp ridges in some mountainous areas. Some divides, on the other hand, are a little bit harder to pinpoint if an area has little topography, for example, and no change that is apparent. Sometimes this also happens when the area is pretty subdued. Because water overall will flow downhill almost always, the outlet, meaning the place where the stream exits the drainage basin, is typically at the lowest elevation of the whole drainage basin or the watershed. Drainage divides range in scale from a small ridge separating two gullies on a hillside to a continental divide, which will split an entire continent into enormous watersheds. So, for example, the Mississippi River has the largest drainage basin in North America, carrying about 40% of the flow in the U.S. The top image, as you're seeing here in the slide, shows you the different drainage basins that we have in the U.S., and the Mississippi drainage basin itself is subdivided into 6 other drainage basins, as you're seeing in the lower picture. One of those drainage basins is the Missouri River Basin up here in the northwest part of the Mississippi River drainage basin. And within the Missouri River Basin, there's also a division. One of those divisions makes up the Yellowstone River drainage basin, and that is also kind of to the northwest or west middle area of the Missouri River Basin. So these drainage basins, continue to subdivide and subdivide and subdivide based on the different topography that allows for the precipitated water to fall to either one side of a ridge or a topographical high or the other. So this link here is going to take us to a super cool map representing the streams of the U.S. Let me bring it up for you. As you're seeing in the map, it shows those rivers in the U.S. and the way those rivers feed into larger streams, so as they are tributaries to larger rivers. So it is a very complex image, as you're seeing. It represents the Mississippi River drainage basin clearly, but as you're seeing also, there are many other ones exhibited over here. So in Idaho, we are part of the Columbia River Basin, but within the Columbia River Basin, there's also subdivisions for the Snake River Basin, for example, or the Coeur d'Alene River drainage basin and whatnot. Also, there's a pretty cool video down here that shows kind of the development of the Missouri-Mississippi River drainage basin. So let's watch it real fast so you can see how those streams kind of feed into the larger ones and make up the overall drainage basin. So a river system will include not only its network of stream channels, but also its whole drainage basin. It can be divided into 3 main zones, which, although are all happening at the same time, one will dominate over the other 2 at a specific area. So those 3 zones are going to be an erosional zone, represented by the top left picture, as you're seeing in the slide over here. The erosional zone, or also called the zone of production, is where sediment is produced as it's being eroded. There is another zone called the sediment transport zone, represented by this lower left photo down here. And lastly, there is the zone of sediment deposition, which is represented by the lower right photo down here. So most of the sediment is derived from the zone of production, and it's typically located at the headwaters region of the river basin, so somewhere up, typically in higher elevation. Some of it may also come from the bank erosion that occurs, as is the case in the lower left picture, for example. So there has been some bank erosion over here. So some of the sediment production comes from further down into the trunk system area. But most of it does come from the headwaters region. Downstream from the zone of production, sediment acquired by a stream is transported through channel networks along sections referred to as the trunk streams. So that would be this section right here. These trunk streams may rework the channel over time, but overall will keep the sediment volume in balance. So when these are in balance, the amount of sediment that is being eroded from the banks will equal the amount of sediment that is being deposited elsewhere in the channel, which are typically in bars, as we'll look at later within the lecture. So when a river approaches the ocean or another body of water, it tends to slow down. As it does this, the energy of the stream will greatly reduce, and much of the transported sediment will be dropped and hence be deposited. So most of the sediment will then accumulate at the mouth or outlet of the river to form what we call a delta, or it can be reworked by wave action to form some other coastal features. Sometimes it can even be carried far offshore by ocean currents, and so we don't see it right at the mouth of the stream, but the sediment will be deposited a little bit of ways away. This type of sediment tends to be finer ones, as it can be carried a little bit farther than the more coarse material. So the coarser material tends to be deposited much earlier within this longitudinal profile, so it's going to be a little bit closer to the headwaters region or even the trunk stream, and then the finer material will make its way almost all the way, if not all the way, to the mouth of that stream. So drainage systems are interconnected networks of streams and can usually exhibit a variety of patterns. So the pattern that they form is mostly dependent on the rock type in which they flow, or on which they flow. And then they will also be dependent on the fractures or joints that this area has. So the most common pattern is called a dendritic pattern. Dendro means tree, so the pattern resembles kind of like a branching tree. This pattern typically forms when the material underneath is relatively uniform and when its resistance to erosion is relatively low. So typically there's going to be flow of this or of this kind where you have relatively unconsolidated material rather than bedrock, for example. So the bedrock, or sorry, the material underneath the flow is not going to have a large control over the stream flow, but rather the stream will control where it goes. So this pattern again is mostly controlled by the slope of the land rather than by the material underneath. The radial pattern that you're seeing here on the bottom part of the slide, bottom left, it happens as the streams diverge from some sort of central area, like spokes on a bike wheel. So it typically develops on isolated volcanic cones, like cinder cones or stratovolcanoes, and it also happens when you have uplifts by salt domes, which we haven't looked at, but you can think of a large dome that has been moving upwards at depth, and so it uplifts the surface, making it some sort of circular pattern. A rectangular pattern is exhibited by many right angle bends, like you're seeing here on the top right of the image. This develops when the bedrock is kind of crisscrossed by a series of joints or faults, and so that is the typical pattern that you'll see. So it is mostly controlled by the bedrock rather than by the stream flow and the slope. And then you have the trellis pattern, which is down here on the bottom right of the picture. And it is similar to a rectangular pattern, but in this case the tributary streams are nearly parallel to one another, and then they have the appearance of kind of garden trellis, which is why we call it that way. This pattern forms in areas that are typically underlain by alternating bands of resistant and less resistant material. And it is a very common pattern for the Appalachian Mountains that are folded. So in this case, the less resistant parts would be the ones where the flow is, and then the more resistant ridges would be the subdivisions between each parallel stream. All right, so now we're going to look at stream flow. So the water in stream and river channels moved under the influence of gravity is going to be moved under the influence of gravity. In slow-flowing water, typically confined as well, the water will move in nearly straight-line paths parallel to the stream channel. So this type of flow is laminar flow, again, in some sort of straight lines where the flow is confined and is flowing parallel to the stream channels. However, this is not very common. Laminar flow is rare in nature, and so most streams will flow as turbulent flows. So turbulent flow will happen when the particles move in a rather erratic pattern, as you're seeing here on the top right. This is more typical, this is a little less typical. Sometimes a stream may appear to have laminar flow at the surface, but near the riverbed and the riverbanks, where the resistance is greatest, there will probably be some turbulent flow that is occurring within the stream. A key factor that influences the type of flow that a stream will have is the stream velocity. And as the velocity increases, the flow will become more turbulent. So in the next coming slides, we'll see what factors will influence the stream's velocity. So flow velocities are typically determined at gauging stations by averaging the measurements taken at various locations across the stream's channel. And typically, these velocities will vary pretty greatly depending on which part of the stream you are measuring. Some velocities will be as low as 1 kilometer per hour, when others may be as fast as 30 kilometers per hour. So there's a great variation. The main factors that will have an effect on the stream's velocity are the channel's gradient, the channel's cross-sectional shape, the channel size and roughness, and the discharge of the channel, which in turn is kind of influenced by the velocity, but we'll look at it in a few slides and you'll see what I mean. So the slope of a stream channel, which is expressed as the vertical drop, or also called the rise of a stream, over the specified distance, also called the run, is called the gradient. So gradient is defined pretty much as rise versus run within a stream. For example, certain areas of the lower Mississippi River have a gradient as low as 1 centimeter of vertical change per every kilometer of distance that is covered by the stream. So very low gradients. In contrast, some mountain streams will have gradients as high as 40 meters of vertical change over 1 kilometer of travel distance. So these mountain streams become 400 times faster than the Mississippi River based only on gradient.